All right, so as we were talking yesterday, I'm going to go back to, before we had a little bit of excitement, right? We're going to go back to the conclusion of the polar bonding and the beginning of the polar molecules, that conversation. So we are in, and I've kind of done it a little bit out of order from the book, but we're just about on page 189, 190 in that area. You'll see that they have some bonding issues that they talk about after they talk about the molecule issues. So remember, polar and nonpolar bonds and polar and nonpolar molecules. The bonds, and we've discussed that already, where there's an unequal sharing between two elements. Okay, the two elements that have a covalent bond with single, double, or triple, that they're sharing electrons. Each one of them gives one into the share, and at times they have none, at times they have one, and at times they have two. And wherever the electrons tend to be, that side of the bond tends to be negative because they tend to have the electrons, and the electrons have a negative charge. Because those electrons may tend to be around one element as opposed to the other, one becomes partially negative because it has the electron. One becomes partially positive because it tends to not have the electron. Remember, this is a sharing, but it's not fair. One element is hogging the electron. Which one is going to hog the electron? Remember from yesterday? What periodic property are we looking at? Electronegativity. So the higher electronegativity, remember, electronegativity is the force that an element exerts to gain an electron. So that element which has the higher electronegativity will tend to have the electron more often than its bonded partner. Because the one with a higher electronegativity tends to have the electron, it tends to have a partial positive charge. Excuse me, I said that wrong. Because it tends to have the electron, it tends to have a partial negative charge, which results in the other element having a partial positive charge. I said yesterday as well, if you look at other textbooks, they will get into whether or not something is a polar or nonpolar bond based upon the differential between the electronegativity of the two elements. There are some textbooks, they teach it this way, and it's not wrong, it's just a different way of viewing it. This text has a different standard. So if you look in other textbooks, occasionally there'll be an electronegativity differential, like both of them are trying to vie for the electron. They both are willing to grab it and pull and fight for it, a tug of war. And the stronger one tends to get it more often. Doesn't mean the weaker one doesn't get it occasionally, but the stronger one gets it more often. And so some books go through and teach it, some courses teach it, and curriculum teach it, that if the difference between the electronegativities is really small, even though they're different, they still consider it to be a nonpolar bond because the sharing is almost equal. Other differences, the difference between the electronegativities is pretty great, and then they call it a polar bond. And then they take it to even a farther extreme. Now, what do you think an ionic bond looks like? We've talked about ionics, right? What about the electronegativity differential? It's not minor, it's not significant, it's huge. And the difference is so huge that some people consider the ionic bond to be a polar, like a superpolar bond. Why? Because the electron never goes back. It spends all its time with the other element. So that's maybe one way to think of it, as a continuum. In other textbooks, very small differential, nonpolar. Larger differential, polar. Super huge differential, ionic. Now for our purposes in this course, we're just teaching it that if you have two elements sharing an electron and they're not the same element, there's going to be some difference in the electronegativity. And that some difference is going to make it polar. Whether it's a just minor polar or a huge polar, we're not getting into that. It's just going to be considered polar or nonpolar. Kind of like the stair-step line. If it's to the right, it's a metal. Or excuse me, if it's to the right, it's a nonmetal. If it's to the left, it's a metal. Are there exceptions, transitions, all that kind of stuff? Yes. But for our purposes, we simplified it. Same thing here. If two elements are sharing and they're different elements, it's going to be some polar relationship. If they're the same element, like a homonuclear diatomic, it's an even sharing, it's a nonpolar bond. Okay? So the difference between the polar nonpolar bonds affects how we determine whether a molecule is polar or nonpolar. Remember, the idea of polarity, having poles, means one side tends to be a charge and the other side tends to be the opposite charge. As opposed to nonpolar, meaning that hey, it's pretty much distributed evenly throughout. Okay, and if it's positive at times, it's negative an equal number of times, and so it kind of cancels it out. That's nonpolar. Polar means one side tends to be charged a certain way, and the other side tends to be charged the opposite. And so just the way that bonds can be polar or nonpolar, so can molecules. And the type of bonds that are in those molecules give us a head start on figuring out whether or not the molecule as a whole is polar or nonpolar. Let's look at a few. We'll actually do the experiment tomorrow, probably. A polar covalent molecule. Polarity means there's a charge differential most of the time. Okay? So think of it that way. It has poles because it tends to have a distinct positive or negative side. So a polar covalent molecule, it's a covalent molecule that has an imbalance in the distribution of electrons throughout the whole molecule. Remember, for the bond, it was the electrons are not evenly shared. For the molecule, the electrons are not symmetrically placed, is a way to think of it. This uneven distribution, or this imbalance in the distribution. There's not a symmetry taking place. And that lack of symmetry creates an imbalance in the charges. And the imbalance in the charges is what a pole is. This polarity comes from the imbalance in the charges. So this definition is in your book, but a polar covalent molecule, it's polar, means there's a charge inequity. There's not an even distribution of the charges. It's covalent because that's the way the atoms are bonded to one another. We looked at this NH3 ammonia molecule. Nitrogen is a column 5 element, so it has an unbonded pair and 3 single covalent bonds to the 3 hydrogens. And looking at their electronegativity, we've said that nitrogen is much farther to the right than hydrogen. Hydrogen's a little bit up, but nitrogen's much farther to the right. And because the periodic property for electronegativity is increasing up and to the right, we said that nitrogen has a stronger, larger electronegativity. It means it's fighting to get electrons much more than hydrogen is. And because it's exerting more force than hydrogen is, the electrons that they're sharing tend to be around the nitrogen. Okay? They don't tend to be around the hydrogen. What that does is it sets up the partial charges around. I'm not going to re-show that whole diagram, but we can see from the little indicators there, the electrons tend to be in the direction of the arrow, meaning they tend to be towards the nitrogen, which creates a positive, partial positive towards the hydrogen. The electrons tend to be towards the nitrogen, so the partial positives are towards the hydrogen. If you look at this, we've got an unbonded pair, and we have a tendency for partial positives here and a 3 partial negative here. Question, is there an even distribution of electrons symmetrically around this entire molecule? No. The fact that I can have a positive edge, a partial positive here, and a triple negative here, in addition to an unbonded pair, means this side of the molecule is very partially negative. So if I were to bring a positive charge, let's say that my pointer here, or my it's a pointer / remote, if I bring this in, let's say that this is a positively charged item. It's positively charged. As I bring it in from screen left towards here, what's going to happen to that molecule? Remember, this side down here is positively charged. This side up here is negatively charged. This right here is a positive charged object. Just think very basically, what is going to happen to that molecule?
Is the negative one attracted?
While the negative is attracted to the pointer, the negative side would be attracted, the positive side would be repelled. So what's it going to do? It's going to rotate. It's going to be attracted. The negative side here is going to be attracted to the positive, and the positive side down here is going to be repelled by the positive. And those two forces of attraction and repulsion are going to work together and cause this molecule to reorient in this way. Okay? Because it has a clearly negative side and a clearly positive side. And so the electrons are not evenly distributed. There's not a symmetry there. As a matter of fact, let's think about it for a minute. This shape, the pyramidal, it's based upon a tetrahedron, right? Right? The central atom has 4 points of connection. If you have a tetrahedral, you have to have 4 bonds in order for it to possibly be nonpolar. If it doesn't have 4, if it's a pyramidal or a bent, it will be polar because it can't be symmetrical. The only perfectly symmetrical shape based upon a tetrahedron is the tetrahedral. Okay? So here's your hint. If it's a pyramidal or if it's a bent, it's polar. It has to be a polar molecule because you have unbonded pairs that throw off the symmetry. Right? If I had a tetrahedral, if I had a CCl4 molecule, and we'll see one of those in a moment, remember, that's perfect symmetry in all directions. Everything's 109 degrees apart. Can't get any farther away because to get farther away means to get closer somewhere else. Because I have the same bond, C to Cl, in all 4 directions, I have perfect symmetry. So let's look at that. A nonpolar covalent molecule is a covalent molecule in which the electrons are evenly distributed throughout the whole molecule. There is an even distribution. To be a nonpolar covalent molecule doesn't mean that you can't have polar bonds. But when you do have polar bonds, they balance each other out. That's the hook. So for example, I'm going to show you this C2F4 molecule. We looked at this yesterday. And yesterday we were looking at it in terms of the bonds. And so yesterday is when we came up with saying, okay, fluorine has a greater electronegativity than carbon, therefore the electrons tend to be towards the fluorine, which sets up a partial negative on the fluorine and a partial positive on the carbon, right? So we have 4 polar covalent bonds. And we ask the question, is the molecule itself as a whole polar or nonpolar? Now hopefully you're looking at this in 2 dimensions, but recognize that this is also the same thing in 3 dimensions because we have 2 trigonals bonded together. We have a nonpolar double bond in the middle, meaning the carbons share those electrons evenly. Do you see the symmetry? Do you see how for every force that's partial negatives are here, 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 and here, that whenever we have a partial negative in that direction, we have a correspondingly perfectly symmetrical negative in the other direction. And so even though this molecule is made up with 1 double nonpolar bond and 4 polar bonds between carbons and fluorines, because it lays out with perfect symmetry, the net result is a nonpolar molecule. Where is the negative side on this molecule? Again, the molecule as a whole. Where's the negative side? Can you draw a line through this molecule and say this side is negative and this side is positive? You can't, can you? It's perfectly symmetrical. And though it has polar bonds, the net result is a molecule which is nonpolar. Because again, there is no positive side or negative side of this molecule. It's showing us a perfect symmetry. So here's the kind of the rules you need to apply to figure out whether or not a molecule is polar or nonpolar. What we're trying to do here is say for a molecule to be polar, if it's not polar, what is it? It's nonpolar, okay? So here's the argument we're making. We're trying to prove it's polar, and if it's not, it's nonpolar. In order for it to be polar, it must have polar bonds. Now that's the way the book says it. I'm going to say it to you this way. It must have at least 1 polar bond. Okay? Because you could argue on the last one we looked at, the C2F4 molecule, that there was a nonpolar bond between the carbons, right? So if you just go with the statement, it must have polar bonds, you come back and say, but they weren't all polar. Okay, that's why I'm giving you the caveat. It must have at least 1 polar bond. If it has at least 1 polar bond, it could be polar. Could be. But then we have to look at the second condition here. The bonds cannot be equal and opposite. So we're looking at symmetry. Okay? It cannot have symmetry. What's the word that means not symmetrical? Pardon? No. Symmetrical To make something, to negate something, you add a prefix to it, don't you? It's not symmetrical, it's asymmetrical. So this is a test for asymmetry. If it has polar bonds, it could be polar. If it has polar bonds and it is asymmetrical, it's polar. Okay. If it has polar bonds and it is symmetrical, it doesn't meet the requirements to be polar, therefore it is nonpolar. All right? You see the logic there? There's other ways of teaching it, but this is the way the book does it. You need to just focus on one of those ways. So you're testing to find out, is it polar? It could be polar if it has a polar bond. Look at the molecule. Does it have a polar bond? Yes. Okay, it could be polar. Look at it for symmetry. Is it asymmetrical? Yes, it's polar. If the answer is no, it does not have at least one polar bond, or yes, it is symmetrical, then it doesn't meet the case for being polar. Maybe you want to think of this in the positive. I haven't thought of that before, but let's try to get the answer to be yes. It'll be a double yes, okay? So I'm kind of modifying the book here. What I've just said has been right up to this point, but let's think of it as I need a double yes in order for it to be polar. That might be a better way for us to logic through this. So if I get a yes and a yes, then it's going to be polar. So think of it this way. Does it have at least one polar bond? Yes. Is it asymmetrical, meaning not symmetrical? Yes, it's polar. Okay? So if you need to think in terms of it's got to meet both conditions, the two conditions would be polar bonds and asymmetry. Polar bonds and not symmetric. If either of those answers is no, it's nonpolar. Let's go ahead and do some applications of that. And here's one of those real quickly. I said we would see the tetrahedral up here again, but here's the difference. It's only a slight difference between a nonpolar and a polar tetrahedral. Remember I said the only one with 4 connecting points based upon a tetrahedron that could possibly be nonpolar is the tetrahedral. It could be. In this case, it's not though. Let's think about the conditions again. Do each of these molecules have polar bonds? Yes, they both do. You see the symbols on them? Every one of these bonds is polar. We have no place where one element is bonded to its same element. We have 2 different elements in every case bonded to each other. Chlorine to carbon, chlorine to carbon, chlorine to carbon, chlorine to carbon. They're bonded between 2 different elements. Which one has the greater electronegativity? Chlorine. It's farther to the right. Which means the electrons tend to be around the chlorine, which means the carbon tends to be the positive side of the bond. The only difference to the one on the right is we've replaced one of the chlorines with a hydrogen. But see what that does to the polarity of the bond? The polarity of the bond now, carbon has a higher electronegativity than hydrogen, so the electron tends to be around the carbon. What does that do to the molecule? Well, over here, all the negatives are the outside, but all the positives are in the middle, but they're all symmetrical. So when I look at the carbon tetrachloride over here, it is a non-polar molecule because all of the distribution of all the electrons is perfectly symmetrical. But if I look over here to the CHCl3 molecule right here, do you see that this is, as we set up around here, partial negative, partial negative, partial negative, partial positive up there? If I do the 2 cases, do these both include polar bonds? Yes. Which one indicates symmetry? This one. Now the way we've reworded the test, do these both have polar bonds? Yes. Which one is asymmetrical? This one. This is the polar. It has polar bonds and it has asymmetry. Another way of saying that, it has polar bonds and the bonds are not equally distributed to cancel each other out. So my HCCl3 molecule is a polar molecule, My HCl4 molecule is a nonpolar molecule, and the only difference is this hydrogen in place of one chlorine. If I were to bring a positively charged object, again my pointer, and I were to bring it towards this nonpolar molecule, what is it going to do? What's my CCl4 going to do? Nothing. It's a neutral charge. It's perfectly symmetrical, it has no poles. Okay, so it's not going to respond to this positive charge coming towards it. But if I look at my HCCl3 molecule, as I bring this positively charged pointer towards it, what's going to happen? It's now going to pivot, and the hydrogen is going to be attracted to the positive, and the chlorines are going to be repelled from the positive. And there's going to be a response. There's going to be a response to the charge, because it's polar as opposed to being nonpolar. Polar means it has a negative side and a positive side, or a partial negative and a partial positive side. And those partial charges react to the charge. It's not as if this is sometimes negative and sometimes positive and sometimes negative. It is, but the vast majority of the times this is negative, this is negative, this is negative, this is positive. Therefore, it has a high probability, a high tendency to be polar like that. Sets up a dipole, which means the molecule now responds to electrical charges. Nonpolar, it does not respond to the electrical charges. Example 5a. So going from the book, 5.4a. We are all the way forward on page 194 now. Classify the SiO2, the silicon dioxide, as a polar covalent or a nonpolar covalent molecule. Okay? So before we can determine polarity of the molecule, we have to first of all determine the polarity of the bonds. Before we can determine the polarity of the bonds, we have to have good two-dimensional Lewis structure, which we then can view in 3 dimensions. So let's start with the two-dimensional Lewis structure of SiO2. What's going to be my pivot atom? Silicon, right. Silicon's going to be my pivot. And we look at that, and we're kind of looking for symmetry, which means we're going to have what? Oxygens are going to be probably left and right of them. This is what ends up happening. Okay, we get rid of those two real quick. So we have a silicon, which has 4. We have oxygen, which column 6, so it has 6. Oxygen's looking for 2, it wants 2 bonds. Silicon's looking for 4, it needs 4 bonds. And we can work that out and get perfect symmetry. And see, this is actually a 3-dimensional Lewis structure. We can tell that because we've gone ahead and we've oriented these 3 things, these 2 unbonded pairs and this double bond, by 120 degrees. And so it shows that perfect symmetry. So you're looking at a 2-dimensional and a 3-dimensional diagram right now. Okay. Now, which has a higher electronegativity, silicon or oxygen? We look at the chart. Oxygen's farther to the right and it's up. So oxygen has a greater electronegativity, meaning the electrons are going to tend to be at the oxygen. So we point to the oxygens. We point to the oxygens, which puts the other end of the arrow with a positive sign. And we know now that the oxygens here are going to tend to be partially negative because they tend to have the electron. And the silicon here is going to be partially positive because it tends not to have the electrons. So the question is, now that we've got the charges, now that we have the bonds, and now we understand the polarities, is the molecule polar or nonpolar? Ask yourself the 2 questions. And again, I'll try to do it on the fly the way we've reworded it. Does the molecule have polar bonds? First of all. Does it have polar bonds? Yes or no? At least everybody bobble. Not everybody has to speak. Yes or no? Are there polar bonds here? Yes, there are. We wouldn't be able to draw the arrows and the plus signs, right, if there were nonpolar bonds. There are polar bonds because there's a difference in electronegativity. So we do have polar bonds. So the first condition is met. The second condition is asymmetry. Asymmetry. So if we think about it in the negative, is this symmetrical? What you see in front of you. Is it the same in all directions? Do the 2 different poles offset one another? Another way of saying it. Yes, they do. They're equal and opposite. They're pointing 180 degrees away from each other. You know, we can't talk about net vectors and all that kind of stuff. Wish we could, but we're not there maybe in your other courses. But these two forces, these two polar bonds are equal, but in opposite directions. So this is symmetrical, which means it's not asymmetrical. Okay? Remember, the condition for it to be polar is you have to have polar bonds and it has to be asymmetrical. This does not meet those cases. So it's not polar, meaning it's nonpolar. Okay? So this is a nonpolar SiO2 molecule. Same questions for an OF2 molecule. Whether you consider how many open unbonded electrons it has in its valence, or whether you look at symmetry, we're going to know the oxygen is going to be the central. We know that two fluorines want to connect to that. Fluorines have a valence of 7. They're called 7 element. We need 2 of them because oxygen has 6 and wants 2, and the molecule lays out like this. It's based on a tetrahedron. It is not a tetrahedral. Right now, without doing anything more, is this a polar or a nonpolar molecule?
Nonpolar.
It has to be nonpolar. The only way it can be polar, if it's based upon a tetrahedron, is if it is a tetrahedral with 4 bonds of the same polarity. Okay? So this, we know right now this is going to turn out to be a nonpolar molecule. But let's go through the steps anyway. There's our 2-dimensional. We're not going to do the 3-dimensional. This is our 2-dimensional Lewis. And as we look at that, we look at oxygen and fluorine. Which one has the greater electronegativity? Periodic table says that oxygen. Is that right? Nope, it should be fluorine. Okay? So those arrows are reversed. Sorry about that. Fluorine has a greater electronegativity. So in your mind, draw the arrows the other way. Fluorine has a greater electronegativity, meaning that fluorine is going to tend to be partially negative. The oxygen is going to tend to be partially positive. So we have polar bonds. But do we have symmetry? As you look at this, there's nothing over here offsetting it in the opposite direction. And over here, there's nothing over here offsetting it in the other direction. So even if those arrows were done correctly, pointing towards the fluorine, it would be the same answer. There's no equal and opposite charges 180 degrees across the pivot from them to balance them out. So does it have polar bonds? Yes. Is it asymmetrical? Yes. Remember, asymmetrical means not symmetrical. Is it not symmetrical? Yes. Therefore, double yes is polar bonds that are not symmetrical. Therefore, it is a polar molecule. HBr, polar or nonpolar. Hopefully right now, you don't even need to do anything else, because the whole molecule is formed around one bond. And ask yourself, is that bond polar or nonpolar? Well, it's 2 different elements, so it's polar. And since it only has one bond, there's nothing to balance it out. So it has to be polar, right? But if we were to draw it out, there's hydrogen and bromine. Bromine has a greater electronegativity, makes the hydrogen positive. Do we have a polar bond? Yes, we do. Is it asymmetrical? Yes, it is. It's asymmetrical. It's not symmetrical. It doesn't have any bond balancing out that bond's polarity. And therefore, this is a polar covalent molecule. Now, why does that really matter to you? Why is it important for you to be able to go ahead and figure out whether or not a molecule is polar or nonpolar? And these, again, are in your book. But here's the big so what. So what is this? Polar covalent compounds. Remember, polar means what? I want you, when you see the word polar, I want you to think of the word charges. Now, nonpolar means charges too, but they're balanced. But the point being, if something is polar, that means there's a charge differential going on. There is a plus and minus. There's a definite plus and a definite minus side going on if it's polar. If it's nonpolar, it's kind of fuzzy on when it's going to be positive and negative, and they kind of balance each other out all the time. Okay? So when you see the word polar, think of charges as opposed to nonpolar being balanced charges. Polar is unbalanced charges. So a polar covalent compound can dissolve polar covalent compounds and ionic compounds. Why? Well, the technical reasons why we won't get into, but just remember this: like dissolve like. That's the big point here for the last part of the module. Like dissolves like. Or solvents dissolve like solutes. That's a little bit later in our course. Right now, like dissolves like. It's redundant, but it works. Okay? Like dissolves like. In terms of polar covalents dissolve polar covalents because like dissolves like. Also, polar covalents dissolve ionic compounds. Why? Because they involve charge differentials. The exact reason why we'll get into later. Right now, just learn like dissolves like. Polar bonds or polar molecules have charge differentials. Guess what? Ionic compounds have huge charge differentials, right? Remember in the beginning of class I said there's the nonpolars with a small, excuse me, the nonpolars with a small charge differential, the polars with a larger charge differential, and the ionics with a huge differential, a huge electronegativity differential, right? So polar covalents, which are based upon charge differential, will dissolve likes, which means they'll dissolve other polars, but they'll also dissolve ionics. Because the dissolving action is based upon charges interacting with charges. All right? So any question on that? Remembering that polar compounds dissolve polar compounds. And polar compounds dissolve ionic compounds. The other side of that is nonpolar compounds can only dissolve nonpolar compounds. So if you have something and it says, will this dissolve? And they give you a compound, you have to figure out, are they both the same type? If it's a polar compound, it will dissolve polar and ionic. If it's nonpolar, it'll only dissolve nonpolar. If I put a polar compound in with a nonpolar compound, they won't dissolve each other. Think of it this way. Water is a polar molecule. Oil is a nonpolar molecule. Why does oil float to the surface? It has a lesser density, which is why it goes to the top, but it won't dissolve into the water. I mean, wouldn't it be simple if you just stir it up and have the oil dissolve into the water and go away? It doesn't really go away, it just gets broken up so much that it's in really small pieces, but it doesn't do that. Oil and water don't mix. Why? One of them is polar and one of them is nonpolar. Now, if water became nonpolar, it would mess up life as we know it. It just wouldn't work. If oil became polar, suddenly you would put water and oil together and they would, and if you mixed it thoroughly, it would be a homogeneous mixture. But because oil and water are polar and nonpolar, they won't mix, and you can stir it up and it can look like it's all mixed up again, but give it a second, it'll separate back out and have oil and water because they're different types of molecules and they can't dissolve each other. Now, there is one exception to this rule, not really an exception, one very unique case that uses one molecule that uses both of these principles, and that's soap. So this is the part of home ec in chemistry where we go, hey, why do people tell you to use soap when you wash your laundry? Why don't you just throw it in there and use water? Why do you use soap when you wash your hands instead of thinking rinsing is good enough? Right? You say, well, because the soap cleans your hand. How? How does soap clean your hand when plain water won't? Well, here's the deal. When you're just washing your hands with water, for the vast majority of time, all you're trying to do is to use the force of the water to take whatever dirt you have and grime you have on you away. But it's not really interacting with the soilant, the thing that's got you dirty. Okay. Because I've got two different depictions. This one down here is a much clearer, more technical way of representing a soap molecule. Looks like a tadpole, doesn't it? Like up here, here's a more generic way of showing it. And all they're trying to show you is that a soap molecule, it's a long hydrocarbon chain. It's a very long molecule. It does look kind of like a tadpole, right? It's got this kind of a, they call it the hydrophilic head, this group up here, and then it's got this long hydrocarbon chain. And as they show in this diagram here, this is a water-hating tail and a water-loving head on that tail. That's one way to think of it. What does that mean? Okay, basically this. Water, we've said, is polar. Notice at the end of this long chain, we have a charge differential. The front of the head, it's polar. It has a charge differential. Likes dissolve likes. Dissolving really just means getting in the middle of and breaking up and being stuck to. That's what dissolving does. Okay, it breaks it up. So on soap, one end of the soap molecule wants to mix with water. But the other end of the soap molecule doesn't want anything to do with water. But stains that you have, soilants, tend to be nonpolar. So the water can't mix with and dissolve the stain, but the long hydrocarbon tail can. And so what actually happens is the tail end of the soap molecule dissolves and hooks to the stain, and the hydrophilic head attaches to the water. And so what's literally happening when you're using soap to clean yourself is the water that's hitting your hand is hooking to and dissolving the head of the soap. Think of it as connecting to the water. And so the water is pulling this end of the molecule down the drain. And this end of the soap has glued itself to the stain. And so it's not the water washing off the stain, it's the water pulling the head, which has a tail which is connected to the stain, down the drain. Okay? If it was pure water, if it was pure ionic, it would never dissolve the stain. If it was pure, this is the polar side, if it was pure nonpolar, it would never mix with the water and go down the drain. You would have oily hands all the time. It's the fact that it has both properties. A soap molecule has a ionic side and a polar side and a nonpolar side. The polar side hooks to the water, the nonpolar side hooks to the stain, and you benefit because the water then can pull the soap, which then pulls the stain. If you just used water, the hope that water molecule can hit those little pieces of stain and knock it off, because that's all you're doing. But the benefit of soap is it cements, think of it that way, it cements the stain to the water and takes it down the drain. So that's a practical consequence of polarity or non-polarity of the molecule. There's lots of other applications, but this is one that probably, is most helpful for you to think about in how does this all work.